Good morning, everyone. Thank you for joining us so early in the morning. So glad to see all of you here. So today my talk is going to be on machine learning on embedded things. And I will cover the value proposition, some of the key challenges that we are facing. How do we bridge the gap for the challenges? We'll wrap up with a demo and I will summarize. So to talk about the value proposition of machine learning on embedded things, what we really need to think about is the value proposition of edge computing. So I will frame this in terms of the three advantages edge computing has over the cloud. So I have this statement up there, which is quite bold. It says edge computing is the new cloud. So let's see whether it's really true. So the first thing about edge computing, it promises for more responsiveness. And if you see my diagram on the slides, you will see that there's one model on the left-hand side, which is cloud computing, where everything is running on the cloud. And the sensors are just sending data up and waiting for the cloud to return the results. So edge computing promises more responsiveness because some of the processing can be shifted closer to the devices. So that means the distance that the data has to travel is shorter. And because of that, you can respond much quicker. Another key advantage of having edge computing running on servers that are nearer to the devices is that the devices can perform local decision-making. So rather than waiting for the cloud to do some kind of centralized general decision that may or may not apply to the particular location the user is, the edge server, because it's located much closer to the user, sometimes it's located on the user, it can perform very local, user-specific decisions. So that's one key point. Another key benefit that edge computing promises, it's more resilience. So if you think about this, when we have a centralized data center that is somewhere located in some central area, it is servicing the whole country. It's probably servicing a lot of devices, a lot of systems. So if for some reason that goes down because of power outages, because of some kind of disasters, then everything else is affected. So what edge computing promises is this divide and conquer approach, where basically the processing is distributed across many different devices, across the servers. So what happens is you can share the load across these servers. So if you see the diagram at the bottom, instead of having one single data center shouldering all the load, we can actually have multiple little sub-data centers or even sub-fork nodes or edge nodes that process whatever that's needed. And if one of them, for some reason, is overloaded or goes down, powers down, then the other can take over. So that is called load balancing. At the same time, when we add more of these servers, we can scale. We can scale towards having more responsiveness and also more failover. So that's the second key advantage. And finally, perhaps one of the most important for users is increased privacy. So I have this example, this screenshot of Care.ai, which is a company that is under Google. So what they offer is this little device that you install inside the patient's room. So you can see the picture in the middle. It's a little bit small, but you can probably see at the corner, there is a little white color thing. That is the device. And not only does that device have sensors and it can sense the patient's condition in real time, it actually contains edge computing. So what it does is there is a TPU, a Google Tensor Processing Unit in there that does the real-time processing in the device itself. So as a result, any sensitive patient information, such as a video feed of the patient or their vital signs, does not need to travel to another location. It is processed right there and then. And this is important because we are doing this physical separation of the data, and we are doing this, we call this access and scope. So we are limiting the access of the data just to the device. And all that is transmitted across the wire, perhaps to the nurses or the doctors, or even the patient's relatives, is just the diagnosis, so something that is more less sensitive to be shared. So only devices within the range will receive the data. So this perhaps is one of the key advantages of why people say edge computing is the new cloud. So because of these key advantages and many more that I haven't mentioned, edge computing has grown in importance. So the projected global value is to increase from 3.5 billion from last year, US dollars, and this is global value, not just US, with a rate of about 7.4% growth. And that to me is quite okay, it's not super aggressive. It's going to grow to 43.4 billion, so that's a tenfold increase in just a few years. So this is fueled by two things. One is the number of connected devices is going to grow. So as we get more affluence or even more access to technology, there will be more and more devices that have connectivity, some sort of way to transmit or receive data. So there's 29 billion connected devices by 2022. And 75% of enterprise data could be created and processed at the edge because of the advantages that I talked about. And finally, I'm sure many of you have heard of 5G. So what 5G promises is two things. It promises very short latencies. So people are talking about 10 millisecond latencies. You see the projection by IBM. That is very, very fast. And not only is it fast, the amount of data that it can carry is going to be a lot more than what 4G can support. So imagine you have all these connected devices. They are using 5G connectivity. They are able to send data back and forth, not only to the cloud, but also to each other. And when they send data to each other and those devices perform some machine learning, that is edge computing. So coming back to our talk, the subject of our talk is machine learning on embedded things. So for the rest of the talk, I'm going to focus more on the machine learning side. We're going to talk less about edge computing. That is just to set the global picture for you. So one thing that cloud computing has grown significantly, not only because of the cheaper hardware and the investments that have been made by various companies like Google and Amazon and Microsoft, one of the key areas that has fueled the growth of cloud computing is big data and AI. Specifically using deep learning models to solve complex problems that have not been solved before by traditional computing. And if we think about the volume of big data that we are under today, the volume of edge data, which is data created by these connected devices, is just going to grow significantly, right? Just imagine the significant growth of devices. The devices are going to produce data. Where is the data going, right? So the key question we want to address in this talk today is, can we actually port deep learning to edge computing? Can we actually take it from the cloud, transfer off to edge computing, and just call it, okay, we're done, right? So that is really the question, the challenge that edge computing faces today. So I wanted to check what your opinions are about the challenges, potential challenges of running computing, machine learning specifically on edge devices, such as your wearables or even smaller computers, Raspberry Pis that are positioned in areas nearby. So we're going to launch a very quick 30-second poll just to get some of your thoughts. And I would really appreciate if you can spend maybe a couple seconds and give your responses. I know it's early in the morning, so if there's no responses, I'll just continue in my talk. So we'll just wait. You can use the URL pollev.com ISS 2020 to try to add your responses. It is a free text. So I'll give about 30 seconds. So basically, we're asking, what do you think are the challenges for running ML on edge computing? Okay, we see power, privacy, okay, lack of power. Yep. Uncertainty, bandwidth, latency. Good, good, very good. Okay. Thank you so much for the responses. It's such an early session. Sometimes I worry that people are not awake yet, but wow, everybody is responding. Good. So we'll just give a couple more seconds for any more responses, and then I will summarize. Good, speed, privacy, computing. Okay, I think I'll just start talking about the responses. And as you can see, power, speed, latency, computing are the biggest concerns, the biggest challenges. And indeed, so I will ask the question, why do you think these are the key challenges? So let me move back to my slides. Thank you so much for the responses. So because these deep neural networks are heavyweight, right? So that is the key reason why computing, latency, and computing power is specifically is the key challenge. Because what we're trying to do here, we're trying to take the deep neural networks that have been trained from the cloud and somehow cram them into these devices and expect the same level of performance. And I'm going to just briefly introduce why that is not a reasonable expectation. So for those who know about deep neural networks, this section may be a little bit repeat information for you, but for those who are not familiar, I'm just going to use this to set the problem. So deep neural networks are heavyweight. So before we can talk about why they are heavyweight, we need to talk about what they are. So deep neural networks essentially are layers of mathematical operations that are performed on input data. So I have here a cat picture. This cat picture is just little pixels in the image. So what happens when you feed the pixels to the deep neural network? So a deep neural network generally can go to 20, 30, 100 layers. So what we see here are not just 3 layers. Actually, each one is a collection of layers. So the very first layers would just be responsible for the low-level features, such as the shapes, curves, sharp edges, right? And then these will be detected and fed into the next level, which will try to detect ears, whiskers, eyes. So these are mid-level features. And then finally, these are going to be composed into high-level features. So once you compose the ears, nose, and eyes and whiskers, they will be composed into maybe a cat, maybe a dog, maybe a person, or some kind of monster, I don't know, right? So finally, the result will be cat or no cat. So think about this in terms of layers of mathematical operations, and they are necessary. They are the way that deep neural networks have been designed from the ground up, have been trained. Okay? So because we have many layers, imagine each layer is doing a lot of computations. Computations usually need these things called parameters. And they are just basically constants that you use to multiply and add from the input, right? So if you think about it, every layer has many parameters. Every parameter is about 4 bytes, right? And if we handle more complex domains like recognizing human behavior, right? Because not everybody needs to recognize cats, right? It's interesting, it's fun, but it's not really applicable to industry, for example, right? Except if you are in the pet industry. But so if you are going to recognize human behavior, like what is this person doing? Is this person running, walking, or about to collapse, right? For healthcare scenarios. So you need even more parameters, more complex neural networks. So in this graph, if you notice, the bottom lines, the blue lines and the yellow lines, they are academia. So basically people sitting in, doing research and focusing on a particular problem, but it has not been productized. In order for you to productize this so that it can be run in the real world, see that you need to actually increase the level of parameters. So the number of parameters in the green line are what our big companies like Google, NVIDIA, Baidu are doing. They have to boost up how the complexity of the neural networks. So almost perhaps by a factor of 8, right? So if you take as a back of the envelope calculation, 30 megabytes will only give you 1 million parameters. And that's 10 to the power of 6. So if you need to go to 10 to the power of 12, that's order of magnitude, 6 times. So that's like billions, right? Or trillions. So you can just think the heavyweightness is even more as we need to productize these deep neural networks. And finally, not only are they heavyweight in terms of volume, they are heavyweight in terms of the things they have to do with the parameters. So these floating point operations, basically operations adds and multiplies with these parameters, will just increase. So this graph is a pretty common graph that we see for image recognition neural networks. So recognizing cat, dog, and kangaroo. So you can see that there is a general trend. As the accuracy goes up, the number of parameters increases. So the size of the circle increases. Also, the number of operations on the x-axis increases. So you can see there is a proportional increase. In order for the deep neural networks to do their job and to do a good enough job, because 80% accuracy is actually means you get 20% wrong all the time. It's not really that good, right? So just imagine how heavyweight, the heaviness of these deep neural networks, right? As a result, basically the state-of-the-art hardware that is used to run these in the cloud, remember this is done in the cloud, deployed in, let's say, Google Colab, the servers, right, Amazon. These are basically, we're talking about trillions of floating point operations, see? Not one, not two, not billion, but trillions. So this is the benchmark that these hardware are using, right? 4.7 trillion operations, 9.3 trillion single means you cut down the precision by half, right? And if you look at the very last column on the right-hand side, the memory bandwidth is in gigabytes per second. So in order for these neural networks to actually do their job in enough responsive time to react to the user, let's say I'm detecting elderly falling, right? I need to be able to detect it within a certain time. I cannot just use 1 hour to detect it, right? So if you try to run this on the Raspberry Pi, it probably takes 1 hour, and maybe the Raspberry Pi, you need to replace it, okay? So we're talking about this kind of scale for embedded devices. So I have on my left-hand side, we call this the super embedded device, because it's actually not an embedded device. It's a computer. It's a 4 CPU, 1.5 gigahertz computer. It can do 8 flops. So I can count the number of flops with my 2 hands, right? Compared to trillions, this is like really sad. And then it only has at most 8 gigabytes of RAM if you somehow do some tricks to share it with the GPU, okay? Because you can't have all 8 gigabytes. You still need some to run the OS. You still need some to run your app, right? And this is considered the superpower device, the Superman really. So most of the time, the everyman device, the everyman embedded device is on the right-hand side. It is an ESP32, which is what I will show in my demo. It is only 40 megahertz, 4 megabytes flash, and the RAM is really tiny. In fact, later in my demo, you will see that I'm doing some tricks to be able to run my neural network on it, but it's possible, okay? So that's a more common device because cost, connectivity. It supports Wi-Fi and Bluetooth, Bluetooth both low energy and Bluetooth normal. So it's actually very easy to integrate into IoT scenarios. And here's another example. This is a mid-range. I know the font is a bit small, but just to give you an idea, it is somewhere in between the very superpower Raspberry Pi and the very tiny ESP32. This is also quite common. It's an ST Micro 32 series. Okay, you'll see this a lot in embedded things deployments. So we are talking about this kind of everyman device, right? Everything. It's cheap enough to be part of the 20 billion devices, right? You can't imagine 20 billion of those NVIDIA graphics cards running around. They're too heavy. They require a lot of power, okay? So as many of you have highlighted, there is a huge performance gap. The performance gap on the left-hand side is we have these neural networks that are so powerful, so versatile, trained by these scientists at Google, at Amazon, and they do amazing things, right? We rely on them every day when we do navigation, when we try to do translation, machine translation. But these have to run on the cloud because they are very heavyweight. And then on the right-hand side, we have these tiny devices that are going to be so widespread, everybody's going to have them in their pocket, but they are so limited, right? How do we bridge this gap? Okay, so I would suggest 3 things that are being done today to bridge this gap. And this part is going to be a very important section of this talk because we are actually talking about what ongoing research is being done and what you will actually see in the near future. Okay? So two of these things are very common sense, right? Because something is too big to fit. Let's say you have a lot of luggage and you try to fit in your car's trunk is too small. So what do? You shrink your luggage, right? You throw away certain things that are not needed, like the extra t-shirt or the extra makeup kit, those things you don't bring the snacks. So same thing, we try to shrink neural networks. We try to take them, maybe they are doing too many things with the floating point operations. I do not need so many decimal points. So maybe I can just use integers. So instead of 4 bytes, I use 1 byte, right? So TensorFlow Lite has this toolkit, which has been around for a couple years. So it's quite stable. I will demo this in later on. Basically, it takes an existing neural network and it shrinks it by throwing off the unnecessary things. However, there is a drop in accuracy because some of these high precision computations are necessary in order for us to get the maximum accuracy, right? But it is an approach. So I have an equation that looks quite complicated, but really we're just throwing away the 0 point and then we are scaling it up, okay? That's one very common area to optimize. The second area is something that's emerging more recently. This was proposed by MIT last year, and actually this year there was a talk about it. So I would encourage you to go Google this talk by this professor at MIT. It's called Once for All Network. So once for all means you train once, then you run it for all kinds of platforms. So what they do is instead of waiting after you finish training to do some compression and try to squeeze as much as you can and make do with the amount of accuracy drop, why not when we train, because when we are training, we are trying to maximize accuracy. So we use the training process to train many different networks at the same time. And not only that, we try to say this part for the cloud, this part for running on the mobile phone for Android, this part for running on ESP32. So you are trying to basically put all your eggs in one basket and train at the same time. Okay? So this is also quite promising. Research has shown, also for image recognition, that it has boosted it by about 3%. And 3% doesn't sound very much, but actually it's quite a big increase. Okay? So what they do, after they train, they do some search to say, oh, okay, this subnetwork has the highest accuracy to run on ESP32. This subnetwork has the highest accuracy to run on cloud. So they basically front load all the work in the beginning, in the training time. So training does take a little longer, but you pay the upfront cost because you know that I cannot just simply run my neural network on the cloud because I have to be able to do some inference locally and get some result, then I can consult the cloud, okay? So that's one area. We're just trying to get rid of the extra baggage or try to pack our baggage in a way that can fit on a smaller car. The second way is also very popular because it's easy. Easy because all I do is I strap on a boosting pack. So I strap on a jetpack, right? Because usually I cannot run, right? Or I cannot fly. So in order for me to fly, I will strap on a jetpack that lets me fly. So this picture on the right-hand side, you see Raspberry Pis and certain boards, and they have little things plugged to them. They have extra things. So the blue color stuff and the gray color on the top right-hand, I know the picture is a bit small, but you can sort of make it out. Those are the extra jetpacks. So you boost your existing embedded device with a GPU. Easy, right? I just run everything on the GPU. The embedded device just behaves as normal. It doesn't have to grow any extra wings. So this actually gives about 4x to 10x speed up, but you pay the cost, right? These extra jetpacks are actually quite expensive. They cost, the Google's TPU costs about $100 US. Maybe the price will go down eventually, but it is an investment. Finally, another exciting development is a lot of companies, startups, and even corporations like Amazon and Azure, they are coming up with pipelines for these kind of scenarios. So what they do is they built in, previously you have pipelines for training on the cloud. We call this big data, right? So now we have pipelines for training on small devices. And we call these ML, embedded ML pipelines. So I have this example, Edge Impulse. It's a very exciting startup. What they do is they have a one-stop shop for you. So they target basically people who are embedded engineers, don't know much about ML, don't have time to learn, right? But they know embedded, they know how to set up an Arduino and let the LED blink, right? So what they do is they created this web page, this free service where you sign up and you can train your gesture recognizers. You can train, they have one that recognizes different brands of whiskey and beer. So you can train little things. Basically what you do is, as an embedded engineer, I know how to collect data, but I don't know what to do with the data, right? I don't have my data science background. So I'll use this service to collect the data, label it, say this part is for beer, this part is for whiskey, right? I know how to label it because I can recognize it. And then I use their tools to build what we call impulses. And impulses are basically just classifiers that say, this is beer, this is whiskey, this is fake beer, this is water, right? So they have this pipeline that even goes all the way down to an Arduino library or a C++ library, which means you can run it on SCMicro, right? Or a WebAssembly, which means you can run it on the cloud. You can run it on anything that supports Node.js. Okay? So this is a very exciting development to keep an eye on. You can sign up for the service. It's actually great. If you don't have an embedded device, you can actually use your mobile phone to train. So you can even try it out without having to buy or prepare the right device. And then another little advancement, actually I'm using this today, is called Eloquent. Eloquent TinyML and Eloquent Arduino. Those are the two libraries that if you know a little bit of ML, or if you just want to tinker around and you have an Arduino lying around and you want to try running ML on it, you can actually use this very simple wrapper. It's a helper library to run your TensorFlow neural network on your device. And this is what I will show in the demo. So what I have here is the link that I shared on the slides. Basically, this is on the GitHub repo. And what I did was I have images that look like this, okay? So this is a person, I got this screenshot from the web, and he is wearing a mask, okay? Then I also got some pictures. This lady is not wearing a mask, right? So she's very not compliant, okay? So I have all these pictures, and what I did was I took them and I trained a neural network, okay? So this is a very simple neural network. I chose this architecture because it is simple enough to work, right? I take this and I ran TensorFlow-like quantization and deployed it onto a device like this. So this is an ESP32, and basically it supports Wi-Fi and Bluetooth, so it's very flexible, and it has some touch sensors as well, okay? So I will just show you what I did. My screen is too small to show the code. So what I will probably do is I will just show you the video of my demo first, okay? I'll maybe do a full screen. So I have this script on my laptop, which I run. It's a Python script, okay? And you see that it took a screenshot of my face. I actually took this last week when I was here. And on the bottom corner, you see this is an ESP32. I had my iPhone kind of pointing at it, right? And was looking at the output of the ESP32. Currently, it says 0.613, which is just the previous reading, okay? So what I expect when I see this is the first step is going to do my laptop will do the pre-processing for the ESP32, okay? For reasons that I will explain later, right? It does the pre-processing. So let me show you what the pre-processing looks like. Basically, it will shrink the image after it's done face detection. So here's the pre-processed face, which is just a small fraction of the image that will be passed on using Bluetooth to the ESP32. Okay, so this is what the ESP32 will receive. It will receive a string of numbers. Okay, and I already have my hint here. It says no mask. Actually, what we're looking for is on this bottom corner, which is very hard for you to see, I know, is that it will show 0.781. Okay? So it detected, so the 7.7 display actually changed, but it's a little bit hard to read for you right now. Okay? So the next test case is actually to do it without, with a mask, okay? So you see, if I continue on the video, okay, I will do another capture using the webcam on this laptop. And now I'm wearing the government issued mask, right? The white color one that everybody wears, right? So I'm wearing the government issued mask, and then it will take the same picture. Now it does some face detection, shrink this to 10 by 10, right? And feed this to the ESP32. So the output hasn't changed yet, but you will see it change, okay? So now it has changed, okay? So it has changed to 0.060, okay? So the 7-segment display is just a way to display the output. It's not really part of the neural network, but what happens is, you see here, it's slightly blocked by my terminal, but there's some data that is going to the device, and it's actually doing the functionality, okay? So I will just show you a little bit of the code, just a walkthrough of it, okay? So again, what we have is we have these input images, okay, right? And then I trained this on the cloud. So this is a Jupyter notebook, okay? The words are too small for you to see, but it's Python code that I run on the cloud, okay? I ran it on Google servers. So you see the same picture is here. I'm doing some pre-processing of it, right? I used OpenCV to do the pre-processing, okay? So all this code is available on GitHub. You can see how I did this, okay? So this is an example of the type of image that we get after pre-processing. So let me scroll down to the training of the neural net, which is more interesting, okay? Okay. So this is the neural net, okay? Let me just scroll a little bit more. So here's the string of numbers I was talking about. This is actually what ends up being fed to the device, a string of 8-bit numbers, okay? So each one represents the grayscale value of the image. So there are 100 of them because my image is only 100 by 100, right? I will talk about the shrinking of the image shortly, okay? But you can just imagine this is going to be sent to the device, and what the device will do is it will run a neural network and it will give me a number, like 0.781 or 0.06, right? So that is basically machine learning, right? So here's the architecture, a bit small to see. I'm using Keras TensorFlow, right? Just three layers, okay? Actually 2 layers. One of them is just to flatten it. I'm using this thing called a separable convolution, and you can read up a little bit more about it. But when you train neural networks to run on small devices, you have to try to pick cheaper networks, cheaper layers that can run with fewer operations. So this is a version of convolution that can run with fewer operations. I have more details in the README file that on the same web page, okay, on the same GitHub repo. So I trained this. So training is no different from training on the cloud, okay? But what is different is this part, okay? The quantization to TensorFlow Lite. And this is probably too small for you to see, but there is a library you can use called TF Lite Converter that you can use to run and convert your model into TensorFlow Lite. So you don't have to do it by yourself. You can actually use TensorFlow to do it, right? So this is a key thing you want to take a note of. It converts a TensorFlow model to a TensorFlow Lite model. Now, of course, I don't have to do it this way. I can use Eloquent Arduino. So Eloquent Arduino is basically one of the libraries that helps me generate the C code from my TensorFlow model. So I get a TensorFlow model, which is run on the cloud, but I want to run it on my device. So I use this to convert into C code, okay? So it does the conversion. The code is a bit small, but it's very simple. I just do one call, port, to port it, okay? And you will see here's an example of the result of porting. It's a bunch of gibberish numbers, right? It looks like just a string of 1,000 numbers or 3,000 numbers. So what this is the TensorFlow Lite file format, but in terms of a C array. Okay, so they take the file format and they just create every single byte is an array. So this is not readable by human. It's not readable by the device as well, but you can run the TensorFlow library on the device to read it, okay? So this is actually my model, my weights as well as the architecture of the model, okay? Finally, the last part this is the sending of the image to the device. So this is the sendImage.py, right, that I ran earlier to do the video capture. Okay, so the part that, let me see if I can zoom in a little bit. Let's see, view. Yeah, I can zoom in here. So let me zoom in because this part is quite key. I do want you to see this. I think you can see this now. Okay, good. Okay, so this is the part that is really key. Okay, I'm actually sending the data, right? This is the data, okay, which will look something like an array of numbers, right? I'm sending it to the device using Bluetooth serial. Okay, so this is sending it to the ESP32. So I am not computing the neural network here on my machine. I'm actually sending it to the device to tell me what is it going to be. Okay, so this is one link. And then the second link is actually the code that's running on the device. So this is the Arduino code, right, which is running on the ESP32. First, I will include the header file with the bunch of numbers here, right? I'll include here, okay? And I will use this library called Eloquent TinyML, written by this developer. I think he's Italian, okay? But very smart guy. So he wrote this library, right? So basically all I did was I will declare the model right here. Say line 33, there is a TinyML TF Lite model, right? So this is actually his wrapper, his utility library, okay, that I will declare that tells, I set the number of inputs, number of outputs. I also set the data. So later on when I did my Arduino setup call, okay, for those who are familiar with Arduino coding, there's a setup function and there's a function. So the setup function is where you set everything up. Here's where I set up my model. So I pass in that whole 3000 byte array into this guy. He will call TensorFlow library to do the predict. Okay. Finally, when I receive it over Bluetooth, here's the Bluetooth data callback on my Arduino, my ESP32. I will do some scaling, but here's the key. Okay. So for those who are familiar with machine learning, there is this function called predict. So you do model.predict, right? And model.predict is basically taking the input data, right? And then you call the model and then you get a prediction. So this is really what happened when we saw in the video, okay? So this is running on the device itself. And so let's actually switch back to the slides and I can give more details. Okay. So we just covered the slide, the demo, what it does. We train a convolutional neural network on TensorFlow on the cloud, and then convert it using TensorFlow Lite, deploy it to the ESP32 and call model.predict. Okay. So I wanted to, so here's the actual video. I will skip it because we're not going to show it here, okay? But you can watch it in your own time. But I wanted to talk about some of the design choices that I made in order for this to work. Okay? I did image pre-processing, which is the face detection and the cropping, before I sent it to the ESP32. I used OpenCV running on my laptop. Okay? I cropped it, I resized it. This is because I'm following this principle where when you want to run a big functionality on a smaller platform, you need to break it down in chunks. So I've broken out the machine learning part into one chunk that I will handle on a ESP32. I focused on that for the demo. But if I really want to do the edge computing paradigm, I need to also have another edge device, perhaps doing the face detection. Perhaps I can get a webcam kind of edge device that comes with a webcam and it has some built-in functionality to do it very quickly. So this is a paradigm that I need to bring up because this is something we need to think about when we approach machine learning on embedded devices. And then the second thing is I chose to use Bluetooth serial because it's very easy to do and it's quite simple to set up. I could have done Wi-Fi, I could have done other things. So that's another design choice that you have to make when you run on these devices. Okay? And finally, the 10 by 10 input size, which is just taking any ordinary picture and shrinking it to 10 by 10, that was empirically determined. What I mean is that I did some experiment. So I tried 10 by 10, I tried 20 by 20, I tried 32 by 32, and 10 by 10 is actually the best performing one Because when you think about it, when I have a face mask, there's a blob around my face, right? About uniform color, okay? Let's ignore those very colorful and cute masks, but just the government issued ones or the surgical ones, they're just one uniform color. So what happens is, when you shrink the image, this blob becomes very obvious. So it allows the classifier to do its job without having to be very complicated, okay? So another key idea is be careful about what you do with your pre-processing input. Be very specific. You want to try to make the job of machine learning model as simple as possible, okay? So in the last 5 minutes, I'm just going to summarize what we have learned, okay, and what the next steps are. So we covered edge computing because it sets the stage for embedded machine learning, right? Embedded machine learning is basically running machine learning on embedded devices, and it is part of edge computing. And the reason why we're doing this is because edge computing has these 3 promises. But in order for it to fulfill the promises, we need to match this performance gap, right? Where we have all these big networks can do all these wonderful things, but they can't run on these small devices. So I've brought up 3 ways that the gap is being crossed today. TinyML, this is an area called TinyML, TinyML. It's actually an area of research. There's a lot of effort going into this now, especially with the adoption of 5G. People are really trying hard to solve this, being able to run neural networks, deep learning onto small devices, because they can see the potential of it. Right? So those are the 3 things that we covered: shrinking it down, getting rid of the extra baggage, strapping on a jetpack, and also making it smoother for you to develop these things. And if you are thinking about this area, or you just kind of deciding whether you want to look into it, especially if you have investments in IoT, I will have 4 suggestions. One is you break down the problem into smaller chunks. Okay? Instead of training a very complicated beast of neural network to do everything, it's very easy to do on the cloud. But when you come to small devices, you can't afford the memory and the processing to do that. So you train multiple simple networks and you chain them into a pipeline. Okay? Divide and conquer. And also, I would suggest targeting a mid-range or low-range platform rather than just focusing on Raspberry Pi 3 or 4. Because Raspberry Pi 3 or 4 is really not the level of constraints that you will face. The true constraints is when you have to run on something that only has 382 kilobytes of heap of memory. So you really can't do a lot, but it gives you a lot of outlet for creativity, for using TinyML, for using more creative ways to structure your problem. So I suggest the STM32 series, ESP32, Arduino. These are actually more commercially viable as well for mass deployment. And you can have tons of these all doing little functionality. And finally, evaluate if you need to use ML at all. There are certain things that ML is good for, which is to find latent patterns between cross-domain things. For example, if I have a signal or if I have information from audio signal, I have information from text, I have information from image, ML is good for marrying all 3. And it finds the patterns because it doesn't care what the domain is. But it's not very good for filtering, for pre-processing, because those things are in the traditional domain of those non-machine learning domains. They have been well established. There are DSP chips that can do signal processing very quickly, designed very well, very reliable. Use them. In fact, a lot of these new chips are coming up with DSPs, TPUs, as well as general purpose CPUs, all in one board. So that is the direction that we are seeing in this edge device, that it will come with specialized chips. And finally, I can't end this talk about edge computing without a plug for our grad cert. So I teach part of the Architecting Smart Systems grad cert that is offered by NUS ISS. And this is really where we focus a lot on bridging the gap between IoT and intelligent systems. So our students focus on building the end-to-end software sensing systems, like automated patient care monitoring. We look at case studies for Industry 4.0, look at transport systems. In fact, if you are curious about one of the outcomes of this cert, go check out the virtual showcase So there is a showcase by one of our student groups called the Smart Air Conditioning Management, Smart Aircon Management. It's going to be run throughout this 4 days. So see what the work that they have done and see whether this is something that you are interested in. And they basically just spend four months, but 10 man days of work. They did this while taking the course concurrently. So everything is done in 4 months. And it's a group of 3 students and they managed to get this up and running. So it's basically they built prototypes. So that's all for my talk today. And thank you so much for bearing with our slight technical hiccups because this is the first talk. Unfortunately, I don't think there's time for questions. So if you have any questions, you can reach out to me. Here's my contact information. And you can also reach out to us and NUS ISS anytime. So thank you so much and have a nice day.